Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The dawn of the 19th century found optical science wrestling with profound limitations. Telescopes, microscopes, and other instruments, while marvels of ingenuity for their time, suffered from aberrations and a limited understanding of the fundamental nature of light itself. Phenomena like polarization remained enigmatic, hindering advancements in fields ranging from astronomy to materials science. Within this intellectual landscape emerged David Brewster, a Scottish scientist whose meticulous experimentation and keen insight would illuminate some of light's most intriguing properties. Brewster's early investigations centered on the behavior of light as it interacted with various substances. He became fascinated by the way light reflected and refracted, bending and changing intensity as it passed through different media. These initial forays were far from simple observations. They were carefully designed experiments aimed at quantifying the relationship between the angle of incidence, the refracted index of the material, and the resulting properties of the light. One particular line of inquiry proved especially fruitful: the study of polarized light. Light, unlike sound, is a transverse wave, meaning its oscillations occur in a plane perpendicular to its direction of travel. Ordinary light consists of waves vibrating in all possible directions within that plane. Polarized light, on the other hand, has its vibrations confined to a single plane. Scientists knew that certain materials, like Iceland spar, a form of calcite, could polarize light. However, polarization could also occur through reflection, a phenomenon Brewster sought to understand in detail. He meticulously examined how light behaved when reflected from surfaces at varying angles. Through painstaking measurements, he noticed something remarkable: at a specific angle of incidence, the reflected light became completely polarized. This angle, unique to each material, held the key to unlocking a deeper understanding of the connection between light and matter. This angle would eventually bear his name, Brewster's angle. While deeply immersed in these fundamental investigations, Brewster also possessed a remarkable talent for practical application and a keen sense of public appeal. This is perhaps best exemplified by his invention of the kaleidoscope. While the principles of multiple reflections were known, Brewster ingeniously combined mirrors and lenses within a tube to create an instrument that produced an endless variety of symmetrical and aesthetically pleasing patterns. The kaleidoscope became an instant sensation, captivating audiences with its ever-shifting displays of color and form. It is more than a mere toy. It showcased Brewster's ability to translate scientific principles into objects of beauty and wonder, demonstrating the inherent connection between scientific discovery and artistic creation. The kaleidoscope's popularity served as a powerful reminder that science, when artfully applied, could enrich everyday life. Brewster's academic career began early, reflecting his precocious talent and dedication to scientific inquiry. He secured a position at the University of Edinburgh, a prestigious institution with a vibrant intellectual community. This appointment provided him with a platform to pursue his research and share his findings with a wider audience. He actively participated in scientific societies, presenting his work, engaging in debates, and collaborating with other researchers. These interactions proved invaluable, fostering a stimulating environment that fueled his scientific progress. He was elected a Fellow of the Royal Society of Edinburgh at a remarkably young age, a testament to the high regard in which he was held by his peers. His involvement in these societies extended beyond mere membership. He actively contributed to their proceedings, serving on committees and helping to shape the direction of scientific discourse. This early immersion in the world of organized science solidified his commitment to advancing knowledge and disseminating it to the broader community. Brewster's initial work laid the groundwork for a career dedicated to unraveling the mysteries of light. These early experiments, driven by desire to understand the fundamental principles governing reflection and refraction, set him on a path of discovery that would lead to groundbreaking insights. The observation of polarized light at specific angles of incidence was a crucial first step, hinting at a deeper connection between the properties of light and the nature of the materials it encountered. These early achievements propelled him into the forefront of optical science, establishing him as a leading figure in the field. The combination of rigorous experimentation, insightful analysis, and a knack for practical application defined his approach, setting the stage for further innovations that would cement his legacy. The challenges facing optical science in the early 19th century were substantial. Existing instruments suffered from limitations, and the fundamental nature of light remained poorly understood. Brewster's meticulous approach characterized by careful experimentation and a desire to quantify observed phenomena, offered a powerful means of addressing these challenges. His early work on reflection and refraction, culminating in the discovery of the relationship between polarization and the angle of incidence, represented a significant step forward. His ability to translate scientific principles into practical inventions, exemplified by the kaleidoscope, further underscored his talent and broadened his impact. These initial accomplishments established him as a prominent figure in the scientific community, setting the stage for a career marked by significant contributions to the field of optics. His early academic appointments and active participation in scientific societies provided him with the resources and a platform to pursue his research, collaborate with other scientists, and disseminate his findings to a wider audience. This combination of intellectual curiosity, experimental skill, and a commitment to public engagement defined Brewster's approach and shaped his enduring legacy. His initial explorations were fueled by a desire to move beyond mere observation, seeking instead to establish precise, quantifiable relationships between the properties of light and the materials through which it traveled. Brewster sought to uncover the underlying principles governing these interactions. His initial investigations, far from being isolated academic exercises, were driven by a tangible desire to refine existing optical instruments and unlock new possibilities for scientific observation. His early work, though foundational, hinted at the profound complexities inherent in the behavior of light, complexities he would dedicate his career to unraveling. Brewster's early experiments, therefore, were a crucial step toward a more complete understanding of light, paving the way for future advancements in optical technology and scientific discovery. Brewster's angle became a cornerstone of optical science, providing a valuable tool for characterizing materials and manipulating light. Brewster's work, therefore, represents a pivotal moment in the history of optics, marking a transition from qualitative observation to quantitative analysis and laying the groundwork for future advancements in the field. His involvement was characterized by a genuine enthusiasm for scientific inquiry and a willingness to share his knowledge with others. Brewster's dedication to scientific communication extended beyond academic circles, reflecting his belief that science should be accessible to all. Brewster's early career, therefore, exemplifies the importance of both rigorous research and effective communication in advancing scientific knowledge. His initial efforts, though focused on specific phenomena, were ultimately driven by a broader vision of unlocking the secrets of light and harnessing its potential for the benefit of society. Brewster's early investigations, thus, laid the foundation for a lifetime of scientific inquiry and innovation. His early work, therefore, was a testament to the power of careful observation, rigorous experimentation, and a relentless pursuit of knowledge. Brewster's initial contributions, therefore, were instrumental in shaping the course of optical science and inspiring future generations of scientists. His early research, therefore, stands as a testament to the enduring power of scientific curiosity and the importance of translating theoretical knowledge into practical applications. Brewster's initial discoveries, therefore, were a crucial step toward a more complete understanding of light and its interactions with matter, paving the way for future advancements in the field of optics. Brewster's early investigations, therefore, were a crucial step toward a more complete understanding of light and its interactions with matter, paving the way for future advancements in the field of optics. His focused attention soon converged on a phenomenon that would etch his name into the annals of optical science: the behavior of light at the interface between different media, and, specifically, the phenomenon of polarization. The nature of light, even in the early 19th century, remained a subject of intense debate, while the wave theory, championed by figures like Crucial and Huygens, offered explanations for diffraction and interference. It lacked a comprehensive account of polarization. Polarization, the phenomenon where light waves exhibit directional properties, presented a significant puzzle. Light that had been polarized behaved differently depending on its orientation, a characteristic difficult to reconcile with a simple, undirected wave model. Existing explanations were largely phenomenological, describing the observations without providing a deep, mechanistic understanding of the underlying physics. Brewster approached this problem through meticulous experimentation, a hallmark of the scientific method. He directed his focus on the behavior of light when it reflects from surfaces. He noticed that at a certain angle of incidence, the reflected light became completely polarized. This angle, now known as Brewster's angle or the polarization angle, held the key to unlocking a deeper understanding of the relationship between light and matter. His experimental setup, while seemingly simple, was ingeniously designed to allow for precise measurement of the angle at which complete polarization occurred. He used various materials, from glass to water, carefully controlling the angle at which a beam of light struck the surface. He then observed the reflected light through a device capable of detecting polarization, essentially a filter that only allows light of a specific polarization to pass through. By rotating this filter, he could determine the degree of polarization of the reflected light. The angle at which the reflected light was completely extinguished when viewed through the filter was recorded as Brewster's angle. Through a series of experiments with different materials, Brewster discovered a remarkable relationship to the tangent of the angle of incidence at which complete polarization occurs is equal to the refractive index of the material. Mathematically, this can be expressed as the tangent of theta sub b, where theta sub b represents Brewster's angle, equals n, where n is the refractive index of the material. This equation elegantly connected the angle of maximum polarization to a fundamental property of the material, its ability to bend light. This discovery had profound implications. It provided a direct link between the macroscopic property of refractive index and the microscopic behavior of light at the interface between two media. It demonstrated that light, when interacting with matter, could be separated into components with different polarization states. This separation occurs because, at Brewster's angle, the component of light, with its electric field vector parallel to the plane of incidence, is entirely transmitted into the material, leaving only the perpendicularly polarized component to be reflected. Brewster's angle provided strong evidence for the transverse nature of light waves, meaning that the oscillations of the wave are perpendicular to the direction of propagation. This was a significant step forward in understanding the fundamental nature of light, even before the full development of electromagnetic theory. The fact that light could be polarized at all implied that it was a transverse wave, unlike longitudinal waves such as sound, which cannot be polarized. The elegance of Brewster's finding lies in its simplicity and its predictive power. Knowing the refractive index of a material, one could immediately predict the angle at which reflected light would be completely polarized. Conversely, by measuring Brewster's angle, one could determine the refractive index of a substance. This provided a convenient and accurate method for characterizing optical materials. The implications of Brewster's discovery extended far beyond the laboratory. Understanding polarization is crucial in many optical technologies. For example, many lasers rely on Brewster windows to minimize reflective losses within the laser cavity. These windows are oriented at Brewster's angle, allowing the desired polarization of light to pass through without reflection, thereby increasing the efficiency of the laser. Polarizing filters, ubiquitous in photography and other applications, also owe their existence to the principles elucidated by Brewster. These filters selectively transmit light of a particular polarization, reducing glare and enhancing contrast in images. The ability to control and manipulate the polarization of light has become an indispensable tool in a wide range of scientific and technological applications. Even today, Brewster's angle remains a fundamental concept in optics education. It serves as a clear and accessible example of the interaction between light and matter, illustrating the principles of polarization, reflection, and refraction. Students learn about Brewster's angle as a cornerstone of understanding optical phenomena. Brewster's work on polarization was not confined to reflection. He investigated polarization by other means, including transmission through stacks of glass plates. He found that light transmitted through a series of parallel plates also becomes partially polarized, with a degree of polarization increasing with the number of plates. This phenomenon further solidified the understanding of polarization as an intrinsic property of light, influenced by its interaction with matter. His investigations into polarization by refraction, combined with his discovery of Brewster's angle, provided a comprehensive picture of how light behaves when it encounters an interface between two different media. This understanding was crucial for the development of many optical technologies, from lenses and prisms to more advanced devices such as polarimeters and optical modulators. Brewster's contributions to the understanding of polarization stand as a testament to his experimental skill and his ability to extract fundamental principles from careful observation. His discovery of Brewster's angle, in particular, remains a cornerstone of optical science, with enduring relevance in both theoretical understanding and practical applications. The simplicity and elegance of his findings continue to inspire scientists and engineers working in the field of optics today. His legacy extends beyond the specific discovery. It embodies a commitment to rigorous experimentation and a relentless pursuit of knowledge, qualities that define the best of scientific inquiry. The impact of Brewster's work resonates through modern optics, demonstrating the enduring power of fundamental discoveries to shape technological innovation. The theoretical underpinnings Brewster established regarding light and its behavior paved the way for inventions appealing to both scientific curiosity and popular entertainment. Among these, the kaleidoscope stands out, a device he both invented and tirelessly promoted. The kaleidoscope's allure lies in its ability to generate an endless array of symmetrical patterns from simple objects. Its optical principle rests on multiple reflections within a set of mirrors, typically arranged at an angle of 60 or 45 degrees. These mirrors create a repeating pattern, transforming randomly placed colored glass or beads into intricate, symmetrical designs. Brewster's initial motivation stemmed from a desire to study the polarization of light through reflection. He recognized the potential of this mirrored arrangement to create visually striking and mathematically predictable patterns. The device, initially conceived as a scientific instrument, quickly captured the public's imagination. Patented in 1817, the kaleidoscope became an instant sensation, spreading rapidly across Europe and beyond. Its popularity transcended social boundaries, appealing to both the wealthy and the working classes. The kaleidoscope's social and cultural impact during the 19th century proved considerable. It became a ubiquitous toy, a source of endless fascination for children and adults alike. Its influence extended beyond mere amusement. Artists and designers embraced the kaleidoscope as a source of inspiration. The symmetrical patterns generated by the device found their way into textiles, wallpapers, and other decorative arts. The kaleidoscope's aesthetic appeal resonated with the prevailing artistic sensibilities of the time, contributing to a broader appreciation for symmetry and geometric design. The device also spurred a cottage industry of sorts. While Brewster secured a patent, its widespread duplication proved impossible to control. Numerous manufacturers produced kaleidoscopes of varying quality, making the device accessible to a broad market. This proliferation, though diminishing Brewster's potential financial gains, amplified its cultural reach. The kaleidoscope became a symbol of Victorian ingenuity and a testament to the power of optics to transform the mundane into the extraordinary. Beyond its immediate popularity, the kaleidoscope exerted a lasting influence on design and aesthetics. Its emphasis on symmetry and pattern recognition prefigured later developments in fields such as abstract art and computer graphics. The kaleidoscope's ability to generate complex patterns from simple elements continues to inspire artists and designers today, demonstrating the enduring appeal of its underlying principles. The seemingly simple toy served as a catalyst for creativity, shaping visual culture in ways that continue to resonate. Brewster's fascination with optics extended beyond the realm of entertainment to address challenges in visual perception. His work on the stereoscope exemplifies this, demonstrating his commitment to both scientific rigor and practical application. The stereoscope, an instrument for viewing stereoscopic images, had existed in rudimentary forms prior to Brewster's involvement. However, his improvements transformed it into a more user-friendly and effective device. Stereoscopic images, created by capturing two slightly different perspectives of the same scene, mimicked the way our eyes perceive depth. Each eye views a slightly different image, and the brain combines these two images to create a three-dimensional perception. Brewster's contribution lay in refining the optical system of the stereoscope to enhance this effect. He understood the principles of binocular vision and applied them to create an instrument that provided a more immersive and realistic viewing experience. Brewster's stereoscope employed lenses and mirrors to present each eye with the appropriate image, ensuring proper alignment and focus. This design minimized eye strain and maximized the illusion of depth. His stereoscope, simpler and more compact than earlier versions, facilitated widespread adoption of stereoscopic photography. The device became a popular form of entertainment and education, allowing people to experience distant lands and historical events in a visually compelling way. Earlier stereoscopes often relied on cumbersome designs and required significant effort to align the images properly. Brewster's improvements streamlined the viewing process, making stereoscopic images accessible to a wider audience. His model, with its integrated lenses and adjustable focus, offered a superior viewing experience. This enhanced usability contributed significantly to the popularization of stereoscopic photography during the mid-19th century. The impact of Brewster's stereoscope on popular culture cannot be overstated. stereoscopic photographs became a common household item, providing a window into the world for those unable to travel. Images of exotic landscapes, historical landmarks, and everyday life circulated widely, shaping perceptions and broadening horizons. The stereoscope fostered a sense of connection to the wider world, transforming visual culture in profound ways. Brewster's understanding of binocular vision played a crucial role in his success with a stereoscope. He recognized the importance of presenting each eye with a clear, properly aligned image to create a convincing illusion of depth. His careful attention to optical design ensured that the stereoscope provided a comfortable and immersive viewing experience. This attention to detail distinguished his instrument from earlier, less refined versions. The stereoscope also had a significant impact on scientific visualization. Researchers used stereoscopic images to study complex structures in fields such as anatomy and geology. The ability to view these structures in 3 dimensions provided new insights and facilitated a deeper understanding of their form and function. The stereoscope became a valuable tool for scientific exploration, complementing traditional methods of observation and analysis. Brewster's dual contributions, the kaleidoscope and the stereoscope, highlight his ability to bridge the gap between scientific inquiry and popular entertainment. He possessed a rare talent for translating complex optical principles into devices that captivated the public imagination. These inventions, born from scientific curiosity, left an indelible mark on visual culture, shaping artistic trends and fostering a greater appreciation for the wonders of optics. The kaleidoscope's influence on design and the stereoscope's impact on photography stand as enduring testaments to Brewster's ingenuity and his ability to connect with audiences beyond the scientific community. Beyond the captivating realms of kaleidoscopic patterns and stereoscopic depth, David Brewster extended his optical expertise to a domain of critical practical importance: lighthouse technology. Coastal navigation in the 19th century presented significant challenges, particularly during periods of inclement weather or reduced visibility. Lighthouses served as essential beacons, guiding ships safely through treacherous waters, and Brewster dedicated considerable effort to enhancing their effectiveness. He recognized that improvements in lens design and light distribution could significantly amplify the range and intensity of lighthouse beams. Existing lighthouse lenses often suffered from limitations in their ability to collimate light efficiently, resulting in diminished visibility and increased risk for maritime vessels. Brewster embarked on a systematic investigation of alternative optical systems, seeking to optimize the projection of light across vast distances. His research led him to advocate for the adoption of Fresnel lenses in lighthouse construction. These lenses, invented by the French physicist Augustin Fresnel, comprised a series of concentric rings of precisely shaped glass prisms. This innovative design enabled the capture and redirection of a greater proportion of light emitted from the lamp, concentrating it into a powerful, focused beam. Brewster championed the implementation of Fresnel lenses throughout the British lighthouse network, arguing persuasively for their superior performance compared to traditional lenses. The introduction of Fresnel lenses marked a transformative advancement in lighthouse technology. Their ability to project intense, highly visible beams over considerable distances dramatically improved the safety and efficiency of maritime navigation. Ships could now detect lighthouses from farther away, allowing for earlier course corrections and reduced risk of collisions or groundings. Brewster's advocacy played a crucial role in the widespread adoption of this groundbreaking technology, revolutionizing coastal navigation and saving countless lives. Brewster's contributions extended beyond the simple adoption of Fresnel's design. He actively worked on refining and adapting the lenses to specific lighthouse locations and navigational needs. He understood that optimal light distribution depended on factors such as the height of the lighthouse, the surrounding terrain, and the prevailing weather conditions. Brewster meticulously analyzed these variables and tailored the lens configurations to maximize visibility in each individual case. This involved adjusting the angles and curvatures of the prisms to ensure that the light beam was optimally directed towards the horizon, providing the most effective guidance for mariners. His work on lighthouse technology exemplified his commitment to applying scientific principles to address practical challenges. He possessed a remarkable ability to translate theoretical knowledge into tangible improvements that had a direct and positive impact on society. Brewster's efforts in this area underscored his dedication to public service and his belief that scientific innovation should be harnessed to enhance human welfare. the improved safety of coastal navigation stands as a lasting tribute to his ingenuity and his unwavering pursuit of practical solutions. In addition to his contributions to optics and practical technology, David Brewster distinguished himself as a prolific writer and communicator of science. He recognized the importance of making scientific knowledge accessible to a wider audience, and he dedicated a significant portion of his career to biographical works that celebrated the lives and achievements of prominent scientists. These biographies served to popularize science, inspire future generations of researchers, and preserve the legacies of important figures in the history of scientific thought. Perhaps his most notable biographical work was his life of Sir Isaac Newton, published in 1831. This comprehensive biography provided a detailed account of Newton's scientific discoveries, his personal life, and his profound impact on the development of modern science. Brewster drew upon a wide range of primary and secondary sources to create a nuanced and insightful portrait of Newton, capturing both his intellectual brilliance and his complex personality. The biography became a standard reference work on Newton's life and continues to be consulted by scholars today. Brewster's biography of Newton went beyond a mere recitation of facts and dates. He delved into the intellectual context in which Newton's discoveries were made, exploring the scientific debates and philosophical currents that shaped his thinking. Brewster also examined the social and cultural factors that influenced Newton's career, providing a rich and multifaceted perspective on his life and work. The biography served to humanize Newton, portraying him as a fallible individual grappling with complex scientific problems rather than a remote and inaccessible genius. He authored biographies of other notable scientists, including Galileo Galilei, Johannes Kepler, and Tycho Brahe. These biographical works shared a common goal to illuminate the lives and achievements of individuals who had made significant contributions to the advancement of scientific knowledge. Brewster approached each biography with meticulous research, careful analysis, and a deep appreciation for the scientific process. His biographies helped to foster a greater understanding of the history of science and the importance of scientific inquiry. His biographical writings contributed significantly to the popularization of science in the 19th century. By presenting the lives and discoveries of scientists in an engaging and accessible manner, Brewster helped to cultivate a broader public interest in scientific matters. His biographies inspired countless individuals to pursue careers in science and engineering, contributing to the growth of scientific knowledge and technological innovation. Brewster's role as a communicator of science was as important as his contributions as a researcher and inventor. Brewster's influence extended into the broader British scientific establishment. He played an active role in scientific societies and organizations, advocating for the advancement of scientific research and education. His contributions were recognized through numerous honors and awards, including his knighthood in 1832. This honor acknowledged his significant contributions to science and his service to the nation. Sir David Brewster became a prominent figure in the scientific community, respected for his intellectual prowess, his practical ingenuity, and his unwavering commitment to the pursuit of knowledge. Sir David Brewster's life and career exemplify the multifaceted nature of scientific achievement. He seamlessly blended the roles of researcher, inventor, and communicator, making significant contributions to both fundamental scientific knowledge and practical technological innovation. His work in optics led to groundbreaking inventions such as the kaleidoscope and the stereoscope, captivating the public imagination and shaping visual culture. His advocacy for Fresnel lenses revolutionized lighthouse technology, enhancing the safety and efficiency of maritime navigation. His biographical writings popularized science, inspiring future generations of scientists and engineers. Brewster possessed a rare ability to bridge the gap between theoretical science and practical application. He understood that scientific knowledge had the potential to transform society, and he dedicated his life to harnessing that potential for the betterment of humankind. His inventions were not merely intellectual curiosities. They were tools that had a tangible impact on people's lives. His work on lighthouses directly saved lives, and his efforts to popularize science helped to foster a more scientifically literate populace. Brewster's legacy extends far beyond his specific inventions and discoveries. He embodied the spirit of scientific inquiry, demonstrating the importance of curiosity, creativity, and perseverance in the pursuit of knowledge. His life serves as an inspiration to scientists and engineers today, reminding them of the power of science to address real-world problems and improve the human condition. He stands as a testament to the enduring value of scientific communication, demonstrating the importance of making scientific knowledge accessible to all. Brewster's impact on optics, technology, and the public understanding of science remains palpable, solidifying his place as a pivotal figure in the history of science.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.